Welcome back. In this lecture, we shall consider finding the shear force and bending moment values for a simply supported beam with a uniformly varying load over the entire length. As usual, we draw the simply supported beam with a hinge or pin support at the left end and a roller support at the right end. We label it as A and B respectively. Then we draw a uniformly varying load of value 0 kN per meter at the end A and W kN per meter at the end B. We mark the length of the beam as L meters. We drop the projections from the ends and draw the zero datum lines for shear force diagram and bending moment diagram. We take the end A as reference and mark an arrow pointing towards the right with variable x indicating the distance of imaginary cross section from it. Before proceeding to find the shear force and bending moment values, we need to find the reactions at the supports. For this, first consider the complete beam in static equilibrium and balance the forces in vertical y direction. We get Ra plus Rb equals half times W times L kilonewtons. Let's label the equation as 1 for later reference. Then we consider the balance of moments, say about point B, and write Ra times L minus half times W times L over 3 equals 0. Hence, Ra equals W times L over 6 kilonewtons. From equation 1, we have Rb equal to half W times L minus W times L over 6. Simplifying, we get Rb equal to a third of W times L kilonewton, and we mark the same on the diagram accordingly. Now, we need to find the value of the ordinate of the uniformly varying load at a distance of x from the reference before proceeding for the shear force and bending moment calculations. Let's label the ordinate as question mark symbol. From similar triangles theory, question mark over x equals W over L, giving question mark equal to W times x over L kilonewton per meter. The equivalent point load of the shaded triangular load equals half times x times W times x over L, which is equal to W times x squared over twice L kilonewtons, and acts at the center of the triangular area at a distance of x over 3 from the imaginary section. Here, there's only one region AB for which x is greater than or equal to 0 and less than or equal to L meters. The shear force at x can be written as plus W times L over 6 minus W times x squared over twice L, which is parabolic in terms of the variable x. The double derivative is found to be negative in sign, hence this curve is of a maxima type joining the shear force values at the ends. Putting x equal to 0, we get shear force at A equal to W times L over 6 kilonewtons. We plot the same in the shear force diagram. Also, letting x is equal to L, we get shear force at B equal to minus W times L over 3 kilonewtons, and hence we plot the same in the shear force diagram. We now join the same by a curve and name it accordingly. We find that there's a change of sign of shear force along the length, and at point C it is 0 in value. To find the location of C, let's assign shear force at x equal to 0. We hence get on simplification the corresponding x value as L over square root of 3 meters and label it in the shear force diagram. Now the bending moment at x equals plus W times L over 6 times x minus W times x squared over twice L times a third of x, which gives plus W times L over 6 times x minus W times x cube over 6L kilonewton meter, and is found to be cubic with respect to the variable x. Investigating the double derivative, we find that it is negative in sign, meaning that the curve joining the moment values at the ends of the beam is a maxima type. For getting the maximum value of the bending moment, we take the first derivative of the moment equation with respect to x and equate it to 0 as per the concept of finding maxima from the elementary calculus theory. We know that the first derivative of bending moment at x also equals the shear force at the section, now which is equal to 0, for which x equals L over square root of 3 meters. Hence, putting x as L over square root of 3 meters in the bending moment equation, we get on simplification the maximum value of bending moment as W times L squared over 9 root 3 kilonewtons meter. We hence plot the resulting maximum value and the curve in the bending moment diagram and label it as cubic. In the next lecture, we shall examine the shear force and bending moment values for a simply supported beam with a concentrated moment applied at the center.